Okay. So I'm glad to present you Didong Li from Princeton and Caltech, and he will tell us today about Gaussian processes on Riemannian manifolds. Oh, yes, sorry, from University of California, Los Angeles. Yeah, and he will tell us today about Gaussian processes on Riemannian manifolds and some theoretical aspects of inference related to them. So, Didong, please.
Yeah, thanks. Thank you for inviting me. Yeah, today I will talk about some fixed domain inference for Gaussian process on compact manifold. And this is the joint work with Wenping Tang from Columbia University and Sudipto Banerjee from UCLA. Okay, I'll make it accessible to everyone. So I'll start with some basic definition of Gaussian process, especially in Euclidean spaces. And then I will talk about some existing results about the identifiability of the parameters in Gaussian process. I mean the parameter in the covariance functions or covariance kernels. Also some prediction interpolation results, also in Euclidean space. And then I will move to non-Euclidean domain, which is the main focus is the compact Riemannian manifold. I will show some parallel results on the manifold. Okay, so I'll start with the basic definition of a Gaussian process. So I guess you'll know that a Gaussian process Z on a domain M is a stochastic process such that for any finite dimensional realization, it follows a multivariate Gaussian distribution. That is, so given any finite points x1 to xn on the manifold M, or maybe on the domain M, the joint distribution of Gx1 up to Gxn follows a Gaussian distribution with certain mean vector and a covariance matrix K. We call this mu the mean function, and it's often assumed to be 0. Otherwise, we can just move it to 0. And the K is called the covariance function, or covariance kernel, or covariograph. It has different names. And this K is always a positive definite matrix. That is, this function K is a positive definite function. And so in the first chapter, we assume this M is a subset of the Euclidean space R to the D, where D is the dimension of the Euclidean space. Later on in the second chapter, I will change to the manifold domain. That is, M is a compact Riemannian manifold, not necessarily embedded in the Euclidean space. Okay. Okay, so why we care about this Gaussian process? Because it's essentially very flexible. It's interpretable and it allows uncertainty quantification. And we know that as a Bayesian, so this Gaussian process is a default prior over functions. And it's also the key model in spatial statistics. That is, it models the spatial dependencies in geostat. It can be used for prediction. It's also called kriging in geostat community. Or it can be used in regression. For example, y is equal to f of x plus epsilon, where x is our input, y is the response, and you want to predict y. And this epsilon is a Gaussian noise, follows a Gaussian distribution with 0 mean and tau square variance. And this f follows a Gaussian process with mean 0 and covariance function k. Or if the output is not the continuous random variable, we can use this Poisson regression, where this y follows a Poisson distribution with this density e to the f. And f is the arbitrary function, so it follows a Gaussian process. And also we can do some simple modification to make it work for classification. And we can use it for density estimation. Assume the density of x is p, and the prior of p. We know that this Gaussian process function f is an arbitrary function, but the density function is a positive function. So we need some link function to relate this arbitrary function and the density function. That is the exponential link. So let p be e to the f. And p is the density function, which is positive, then this f can be arbitrary function. And this f follows a Gaussian process. And also we can use this Gaussian process in dimensionality reduction. That is, x is a high dimensional data, is our observation. It's equal to f of z plus epsilon, where z is some low dimensional vector, is called the latent variable. And this f is an unknown function. And this is called the Gaussian process latent variable model. This is also very popular in dimension reduction. And also this Gaussian process is widely used in deep learning and reinforcement learning recently. Also, it is closely related to the kernel method because we can see a kernel function k here. Okay, and then let's look at some popular covariance functions. The first one is a linear covariance function. K of xi equal to sigma squared and times the inner product between x and y. And then the exponential kernel, also called the Ornstein-Uhlenbeck kernel. And there are two parameters, sigma square and alpha. And also the square exponential kernel, also called the Rbf kernel. The only difference between Rbf and the exponential is that there is a square here, x minus 1 norm square. And this is the most popular one, I guess. It's called the Matérn kernel, where this kxy is equal to this complicated formula, where this k nu is the modified Bessel function of the second kind of order nu. And you can see the sigma square parameter appears in all these kernels. It's called the partial seal or the spatial variance. It's basically the pointwise variance. And this alpha is called the range decay or scale parameter. It measures how the spatial dependency decays as 2 points getting far away from each other. And there's a special parameter in Matérn kernel, which is the nu, is called the smoothness parameter. I'll explain why it's called the smoothness parameter. And this nu is missing in the exponential or Rbf. I'll also explain why. And some further definition, a kernel is called the stationary if k of x, y only depends on the difference between x and y. So that basically says that the covariance function behaves the same at all locations across the domain. And then the isotropic kernel is a kernel that depends only on the distance between 2 points, x and y. That means the direction doesn't matter, only the norm matters. Okay, then I'll define the smoothness of a Gaussian process. So we say a Gaussian process Z is mean square continuous. If as y goes to x, the expectation of zy minus ds square is 0. Okay, because both zy and zx are two random variables, we have to take the expectation to make it simple. Okay, that's why it's called mean square continuous. So when z is stationary, then z is mean square continuous if and only if the covariance function k is continuous only at the origin. Because it's stationary, so the continuity at the origin is good enough to ensure the global mean square continuous. So similarly, we can define the mean square differentiable. Okay, so if z of x plus h over h converges in the L2 sense, L2 means the expectation of something square. So if it converges in the L2 sense as h equals to 0, this is just a standard definition of the derivative, right? We call this z mean square differentiable. And there's a nice result that is z is mean square differentiable if and only if k double prime and 0 exist and it's finite. So that means in order to understand the smoothness of the Gaussian process, we only need to understand the smoothness of the covariance function at 0. And moreover, the derivative of z is again a Gaussian process, and its covariance function is negative k double prime. Okay, and then we can define the higher order smoothness. So z is called m times differentiable or m times mean square differentiable. If it's m minus 1 times differentiable and it's m minus 1 derivative, it's mean square differentiable. So it's an iterative definition.
A small question here. Okay. K is what you defined as K0 on the previous slide, yes? So it's a function of one variable.
Exactly, yeah, sorry for the confusion. Yeah, it's the K0. It's the function only it's a single input function, yes. So if it's not stationary, then these results will not hold anymore. It's more complicated. but still you can show some similar results. So this smoothness of K determines the smoothness of the Gaussian process. Okay. So any other questions? Okay, great. And so why we care about the Matérn kernel, or why we like this Matérn kernel? So let's look at the definition of the Matérn coherence function again. So this is a normalizing constant. This is x minus y norm, and this is a modified Bessel function. So clearly this Matérn kernel is stationary and isotropic, right? Because it only depends on the distance between x and y. And what makes it different from other kernels is that, so first, numerically, it's more stable than Rbf. And also, I will give you one example later in this talk. Second, it's not hard to check that if nu is equal to 1/2, then this Matérn kernel becomes the exponential kernel. And if nu goes to infinity, this kernel becomes the squared exponential kernel. So that is, Matérn kernel basically includes these two popular kernels, exponential and squared exponential, or Rbf. And more importantly, the Matérn kernel with parameter nu is nu floor times differentiable. So we need to make this nu an integer so that we take the floor. It's nu floor times differentiable. And if we just plug in this result, the floor of 1/2 is 0. So that means exponential kernel is not differentiable. It's just continuous, it's not differentiable. And if nu is infinity, then the floor of infinity is still infinity. That means the Rbf kernel is arbitrarily differentiable, right? So these are kind of two extreme cases. One is extremely differentiable, one is extremely non-differentiable. And Matérn kernel, the key advantage here is that you have a parameter nu that can exactly control the smoothness. That's the key property of this Matérn kernel. And here I just copied some sentences from Michael Stein's book in 2012. Basically, he argued that because usually we don't have any prior knowledge on the smoothness of the Gaussian process, so it's very dangerous to just choose a kernel with a fixed smoothness. For example, you just use a exponential kernel. That means you're assuming it's not differentiable at all. Or if you choose an Rbf kernel, you are assuming the Gaussian process is extremely smooth. So that's very dangerous if the truth is not that. For example, if the truth is twice differentiable, then what happens? So he suggested to always use this Matérn kernel unless you have some strong prior knowledge. Then you have a parameter nu that you can tune. You can tune this parameter to allow different smoothness. Okay, and later on we will see that the smoothness of the Gaussian process basically determines the performance of the prediction. So that's why we care about the smoothness. And then the problem is how to check the smoothness of a Gaussian process. So we know that for a Matérn kernel, the smoothness is just nu floor. But for a general Gaussian process, for a general coherence function, how to check the smoothness? We rely on this spectral method. Okay, recall this Bachner theorem. It's a very well-known result.
Sorry, may I ask a question?
Yeah, sure.
Back to the previous slide. So you motivate Matérn kernel by its ability to have a variable smoothness, but
yeah.
there are plenty other families with this property. Still, Matérn has some advantage with respect to them. This would be interesting to explain at some point.
I see. Yeah, that's a good point. Yes, there are some other families that you can control the smoothness. I guess there's also another parameterization of Matérn kernel. I'm not arguing that a Matérn kernel is the best among these. I'm just comparing the Matérn with the exponential and the square exponential. And actually, our result here, it works for a general coherence function on manifold later on. I'm not sticking to the Matérn kernel, actually. Yeah, I guess I should mention some other kernels later on. Thanks. Okay, so let's see be a stationary mean square continuous Gaussian process with covariance function k. Then there exists a positive finite measure f. It's called the spectral measure, such that these are Fourier transform holes. And if f has a density function, and the density is given by the inverse formula, and it's called the spectral density. So basically, it's just the Fourier transform, the Fourier inverse transform. And then the nice thing about the spectral density is that Z is m times differentiable if the spectral density satisfies some integral condition. That is, it decays really fast when omega goes to infinity. So omega to the 2m times the spectral density is integrable. Okay, and let's check the Matérn kernel. So for the Matérn kernel, you can calculate the spectral density is of order like omega squared to the negative nu minus 1/2. And you plug in this integral, you easily check that the smoothness of the Matérn is exactly nu. Okay. And then for the Rbf kernel, the spectral density looks different. So it's not polynomial anymore. It's like exponential to the omega square. And it's easy to check that no matter how large m is, so the exponential function times a polynomial is always integrable. So that's why Rbf kernel is infinitely smooth. Okay, and we will see that, so this Matérn spectral density and Rbf density looks very similar to the density function, spectral density on the manifold case. Okay. And then the question is how to estimate the parameters in all these kernels. For example, Matérn, we have 3 kernels, sigma square, alpha, and nu. And for Rbf, we have sigma square and alpha. So for simplicity, we'll assume we are fixing this smoothness parameter nu. I'll explain why later. So assume the nu is fixed. Given data xi and zi, so zi is just the observation of z at xi. We want to estimate the parameter alpha and the sigma square. So it's very natural to consider the maximum likelihood estimator. So we can write down the likelihood as this. It's not simple because we know the Zi follows a joint, follows a multivariate Gaussian distribution. So we can write down the likelihood of the Gaussian. So the two parameters here, alpha and sigma square, n denotes the sample size. Okay. And where this Gn is the vector of our observation Zi, Z1 up to Zn. And this gamma n alpha is basically the value of the covariance function of xi and xj. Okay, and the point is this gamma n is independent of sigma square. Then given alpha, the MLE of sigma square is given by this closed form. Gn is known, gamma n is known if alpha is fixed. Okay, so it has a closed form solution. And what if alpha is also unknown? We can calculate the joint MLE, alpha ML and sigma square ML. This is also computable, but we cannot present a closed form solution anymore. But anyway, the point is that given some data, you can always estimate this alpha and sigma square by either MLE or some other fancy algorithms just to find the estimator. The question is, so assume this true parameter is theta 0, and the corresponding Gaussian process is a corresponding covariance function is k0. And we generate some data or we observe some data from this k0. And then we can use our MLE to find the estimator of theta 0. We call this theta n hat, where this n is the sample size. Then the question is, as we have more and more data, does this theta n hat converge to theta 0? That is whether the MLE is consistent or not. And the answer is no. Unfortunately, no. This is a well-known result like 30 years ago or so. Then the question is, if the MLE is not consistent, can we find another consistent estimator?
I just wanted to mention that you probably should also specify how we collect the data. So is it contained in a finite interval, or is it like spreading?
Yeah, good question. Yeah, I forgot to mention. So it's a infill regime. So you have some, basically you collect some data from some interval, and then you want to predict a value at a location within this interval. It's an infill case. I'll talk about the prediction later. So here is just about the consistency of the parameter. So I'll talk about the interpolation probably in 2 slides. Okay. Any other questions?
Here we're talking about sigma and alpha parameters, not so nu is already excluded.
So this is the general case. Theta 0 is a parameter and theta n hat is the MLE. Yeah, for the Matérn case, we assume mu is known or is fixed.
Mm-hmm.
We're only interested in alpha sigma square. I'll explain why.
Mm-hmm.
Yeah, okay. And then the question is, can we find a consistent estimator? So if MLE is not that, it's not our desired estimator, the answer is not always. And this proof relies on a definition of the equivalent of measures. Recall that 2 measures P0 and P1 are equivalent if and only if they are absolutely continuous with respect to each other. That is, P0, if A is a 0 measure set under P0, it must be a 0 measure set under P1 and vice versa. Okay, and there's a milestone paper by Zhang in 2004, JASA. He proved that 2 equivalent measures cannot be distinguished by any amount of observations. And so for a family of measures P theta with P theta 1 equivalent to P theta 0, then there does not exist any consistent estimator of theta 0. So that is, if there are 2 groups of parameters, theta 0 and theta 1, and the corresponding Gaussian measures are equivalent, then you can never consistently estimate theta 0 or theta 1. And what does it mean in the Matérn case? It's, I guess I should add this. So if P theta is a Gaussian process with Matérn kernel, where the theta is alpha and sigma square, then Zhang proved that the only parameter that you can estimate is sigma square times alpha to be 2 nu, not sigma square or alpha. I'll talk about this in one slide. Okay. And then how to check whether 2 measures are equivalent or not? So we have a very powerful tool. It's called the integral test. I'm not sure about the origin of this integral test. I can just find it in this Junko's 83 paper, this 83 book, I guess. But he also cited another book even earlier. So this is not the origin of the integral test. So I apologize for that. So again, we need to rely on the spectral density. So let F0 and F1 be the spectral densities of measure P0 and P1. Then P0 is equivalent to P1 if, first, this F1 behaves like a polynomial. That is, F1 times a polynomial is bounded away from 0 and infinity. And this R is the polynomial order. Second, this function is integrable. So F2, sorry, this is a typo. So F1 minus F0 over F0 and square is integrable. So that's why it's called the integral test. And the integral is on some the entire RD minus a small disk at the origin. Okay, and the key observation is here that this is if, not only if. And this is very important in the following slides. Okay, and then Zhang 2004 proved that for 2 Matérn GP, with parameter alpha I, sigma I square, and nu is known. Then when the dimension of the domain is less than or equal to 3, two measures are equivalent if and only if sigma 0 square alpha 0 to the 2 nu is equal to sigma 1 square alpha 1 to the 2 nu. Okay, so that means you can never consistently estimate sigma or alpha, but you can always consistently estimate this entire parameter, sigma squared times alpha to the 2 nu, and this parameter is called the microergodic parameter. I guess this comes from the probability theory.
Sorry, but
And this
you,
is from
you probably mean that measures are equivalent or not equivalent on the bounded domain of time, right? Not on the entire space.
Yes. Yeah, but that's enough. That, I mean, if you want to consistently estimate the parameter, you have only finite number of points, right? So that's good enough.
I have one more question about this slide.
Okay.
So for this integral test, I'm wondering if you can put a plus instead a minus here. So does it really need to contain a difference, or does it like measure only the decay at infinity of F1 and F2, and we don't need to subtract one from another?
Oh, Slava, obviously the difference is needed. Because equivalence of measures means that the measures are similar.
Yeah.
To get them similar, you have to close spectral densities.
Oh, okay. Yeah, so I just thought about this as that we have to get the same kind of order of decay at infinity here. And so, yeah, I understand now. If we divide F1 by F1, we just get 1, and this will be a problem for us, I guess, if we don't have anything to subtract from this. Yeah, okay, so.
Yeah, so this basically says that F2 over F1 is close to 1. That is, the two spectral densities are very close to each other at the infinity. Yeah. And so this is John's proof. So that he only proved the case for D is less than or equal to 3. And when D is greater than or equal to 4, this integral test fails. Why is that? Because when D is greater than or equal to 4, we can easily see that this integral is equal to infinity. And this theorem is if. So it doesn't answer you what if it's equal to infinity. So that's why he only solved the problem, this problem when the dimension is less than or equal to 3. But then later on, this Andres has a very beautiful paper in 2010 Annals. He proved the case when the dimension is greater than or equal to 5. Okay, so he proved that when the dimension is greater than or equal to 5, then these two measures are equivalent if and only if both parameters match. So that means we can consistently estimate the parameter. Actually, he explicitly construct a consistent estimator, which is very beautiful, but that's not MLE. MLE is still not consistent, but he construct another estimator. Okay, and the interesting thing happens here. So what if D is equal to 4? So I guess you are all mathematicians. You have observed this D equal to 4 weird phenomena everywhere in mathematics, right? Like in geometry and topology or whatever. So it's still open until now. So when D is equal to 4, we still don't know whether we can consistently estimate these parameters sigma square and alpha. I will revisit this D equal to 4 problem later on the manifold case. Okay. And what about Rbf kernel? It's another popular kernel, right? And for the Rbf kernel, you can easily check that the integral is equal to infinity. That means we don't have this integral test. So it's still open. So this popular Rbf kernel, we don't know whether we can consistently estimate the parameter or not. Unfortunately, right? It's a very sad story. Okay, and then for the identifiability continued, so we focus on the case when the dimension is less than or equal to 3 because that's more interesting. And let alpha 0, sigma 0 be the true parameter with a wrong alpha 1. So that means we don't know the truth alpha 0 and sigma 0 square. We just arbitrarily choose do a random guess on alpha. We call this alpha 1. And remember that if alpha is known, then the MLE has a closed form solution, right? We call this closed form solution of the MLE sigma hat 1n. So it's clear that alpha 1 is wrong. It's just from random guess. And then sigma 1 square n is also wrong. It's not equal to sigma 0 square. However, John proved that although both alpha and sigma squares are wrong, sigma square times alpha converts to the true parameter with probability 1 under P0. So that means even if you do a crazy random guess alpha 1, it's still fine. You still recover the microergodic parameter. And this Kaufman-Shabby biometric paper in 2013, they also proved that the kind of the converse rate of this part. So basically the microergodic parameter converts to 1 at the speed of 1 over square root of n. And also asymptotically is Gaussian. It's like a central limit theorem. It's not that surprising. Okay, and then we conjecture that when d is equal to 4, two measures are equivalent. I mean, two Matérn measures are equivalent if and only if both parameters match. For Rbf kernel, we conjecture that when P1 is equivalent to P2 if and only if two parameters match. I'll explain why we made this conjecture. Okay, and then let's look at the prediction. So given xi, zi, these are the observations, and a new location x0 in the infill case. And the best linear unbiased predictor, also called the BLUP, of z at x0, is just given by this closed form solution. And this is a well-known result. Okay. And then from Stein 93, this is a paper, and the Kaufman-Shabby 2000, this is 1993, this is 2013 paper. They show that, so z hat n alpha 0 is the true BLUP, because alpha 0 is the true parameter. And z n hat alpha 1 is the wrong predictor, it's the wrong BLUP. But the mean square error are asymptotically the same. Okay, so that means even if you have a wrong alpha 1, as long as you stick to the this BLUP in this sense, it's asymptotically optimal. It doesn't matter. So that's the good news after the bad news. Okay.
I want to just add some comment that, like, I think that the best way to intuitively think about this is that our prior assumption with these hyperparameters, it just vanishes as we get more and more data. And so this is because in the end, we end up having something similar anyway,
Yes.
not matter the parameters.
Yes, exactly. Yeah, thanks for the comment. And then there's a similar result by this Kaufman paper. So we only focus on the BLUP under the wrong parameter. And the denominator is the true mean square error. And the numerator is the wrong mean square error. So we assume the measure is this one. And then we calculate the mean square error. And still they are asymptotically the same. Because you can never calculate the denominator, right? Because the true measure is unknown. So this means the wrong error converts to the true error. So basically, these two results show that this mean specified alpha 1 doesn't matter at all in terms of prediction asymptotically. Yeah. So I'll give you one specific example. So consider we have two kernels, K0 and K1. K1 is just Rbf. K0 is a C1 kernel. You can check the spectral density. So this is C1, first differentiable. This is the infinite differentiable. Here's the plot. I just copied from the microscience book. So the solid line is the smooth one, and the dashed one is the C1 case. So there's no obvious sign that these two kernels are super different from each other, right? It looks similar. And what if we do the BLUP under these two coarse functions? And here's the case. So assume we observe this Z on plus or minus delta J, where delta is some just the step size, and J is from 1 to n. So basically, for example, you observe Z at 0.8, 1.6, 2.4, etc. And you want to predict Z0. And E0 square is the true MSE of the true BLUP. And this is the true MLE of the wrong BLUP. This is the wrong MLE of the wrong BLUP. This is the wrong MLE of the true BLUP. Okay. And then, so assume K0 is the truth. That's what I'm saying here. So if K0 is the truth, but we assume it's K1 and we just find the BLUP, what happens? We can see that E1 U1 square over E0 U1 square is like 10 to negative 10. So what is E0 U1 square? It's the true MSE of your wrong estimator E1. So this is the true MSE. And this is the MLE. You think the MSE is the numerator. It's equal to 10 to the negative 10 means that you are over optimistic. So you think the error is very small, but really the error is not that small. And the ratio is 10 to the 10, which is terrible. So that means if the truth is just C1, but you assume it's C infinity, you will make a huge mistake. It's very dangerous. What happens if we switch K1 to K0? So what if the truth is C infinity, but you assume it's C1? Okay, so if K1 is the truth, it's C infinity, and you assume it's K0, which is C1, then this result is like only 30. So that means, so this is your the MSE you think which is correct, and this is the true MSE. So you are very conservative. Maybe the true error is 1, but you think the error is 30. You are very conservative, but this is more tolerable than the first case. You are over optimistic, and the ratio is like 10 to 10.
This is more or less obvious because you, in the first case, you believe your function is analytic, roughly speaking.
Yes.
Because of this super smooth covariance function. So
yes,
if you believe that some function is analytic and it is not, you get in trouble quite quickly.
Yeah, exactly. Yeah, that's a good point. So that's why, so in Michael Stan's book, he's strongly against this Rbf kernel for prediction if you don't know the smoothness as a prior knowledge. To assume it's analytic is very dangerous. You'll make big mistakes in the prediction case. Okay. Yeah, I'll skip this scalable case. I guess I don't have enough time. I'll talk about the manifold version in the second case. Yeah. So let's move to the constraint domain instead of a regular subset of the Euclidean space, like an interval now. So this is the example in the spatial genomics. These are some single cell RNA data. So the color means the cell count, I guess. So the domain is like this. It's a weird shape in Euclidean space. And there's some existing work. For example, this very beautiful paper in 2014 by Ismael Castillo et al. So this is a hit equation-based method. They define a Gaussian process on this kind of constraint domain. And there's another Brownian motion-based by New and et al. So this is a 19 JSSP paper. And also there's a diffusion-based Gaussian process by Didong et al. In 2020. So all these papers basically focus on some diffusion or hit kernel-based Gaussian process. And so also they rely on some certain numerical approximation. And these are kind of the analog of Rbf, very inflexible, very complicated, and very smooth. So we really want something like similar to Matérn, where we can control the smoothness by this parameter nu. And also here's a very well-known result on a Riemannian manifold. If you just simply you simply mimic the squared exponential kernel, which is kxy equal to e to the alpha dxy squared, where d is the geodesic distance. So it's a very natural idea because in the Euclidean case, this is just x minus 1 norm square. Just replace the norm by the geodesic distance. Unfortunately, this one is not a positive definite kernel if the manifold M is not flat. And the exponential kernel also still works. It only depends on the distance between x and y. Also, when the manifold is some sphere, very special manifold, two-dimensional compact manifold, then there are some existing covariance functions, including the Matérn lag with this nu only less than 1/2. And this is motivated by some geostat data, like the geopotential height and temperature, humidity on the Earth. So that's why we care about the domain as a sphere. Okay, and also the brane surface is close to a sphere. These are some existing work on the non-Euclidean domain. I mean the covariance function on non-Euclidean domain. So the main difficulty is that you need to define a positive definite function on the manifold or on the constraint domain. And then here's a very beautiful recent result by Slava's paper. I really like this paper a lot. So they construct this Matérn kernel on a general compact Riemannian manifold in a clean way. So let Fn be the eigenfunction of the Laplacian Beltrami operator on the compact Riemannian manifold, and corresponding eigenvalues be lambda n. And we know because the manifold is compact, then we have this discrete eigenvalue lambda n greater than or equal to 0. And they show that a Matérn kernel or a Matérn GP or Rbf GP correspond to a stochastic PDE. And they solve the PDE on the manifold, then they get this Matérn kernel. Here the Matérn kernel on the manifold with 3 parameters, sigma square, the partial seal, the spatial variance, alpha is the decay parameter, and nu is the smoothness parameter. Okay, and this C nu alpha is the normalizing constant such that the pointwise or the average variance is sigma square. And also they give the spectral density, which looks really similar to the Euclidean Matérn kernel, where you replace this lambda n by omega squared. Okay, and then also they provide the Rbf kernel on the manifold. It's the analog of the Rbf kernel in Euclidean space. Again, it looks similar to the Rbf spectral density. Okay, and then so to conclude that, so on a general Riemannian manifold, we have many well-defined covariance functions. For example, we have this Matérn kernel. So in the later talk, when I mentioned the Matérn kernel or Rbf kernel on manifold, I refer to Slava's version. Okay, and then can we prove the parallel results in the Euclidean space about the consistency or the identifiability of the parameters? That's the question we're asking in our paper. Okay, so that is, given a Matérn kernel on a Riemannian manifold, can we consistently estimate this alpha, a sigma square? And what happens to the BLUP? And like similar questions. And recall that Euclidean space, we rely on the equivalent measures. And to check whether 2 measures are equivalent, we need the integral test. But unfortunately, now the spectral is discrete. We cannot use that integral test. So we need to find a new powerful tool to determine whether 2 measures are equivalent to each other or not. Okay, and not surprisingly, the integral becomes the series because it's a discrete setting. And we call this series test. So let lambda n be the eigenvalue of the graph of the Laplacian operator, and the Tn be the multiplicity of lambda n. And let Pi be 2 Gaussian process on manifold with 2 spectral densities rho I. Then we show that 2 measures are equivalent to each other if and only if the series converges. This looks like the integral test. The only difference is that this is not the integral of rho 2 minus rho 1 over rho 1 squared, and also this multiplied by the multiplicity. This appears naturally when we sum them up. And only one key difference is that here is if and only if, while in the integral test, this is if. So this if and only if helps us a lot. I'll show these key applications of this only if. And then for the Matérn kernel in the Slavas paper sense, we show that two Matérn kernel are equivalent if and only if this parameter sigma square over C nu alpha matches each other. This is the so-called microergodic parameter for the metal case. And this is true when the dimension is less than or equal to 3. This is not surprising because we saw this phase transition when the dimension reaches 4. But this is also kind of surprising because that this phase transition still holds on the manifold. I'll explain more why this d equal to 4 is so important or is so different. And then we also show that if d is greater than or equal to 4, then these two measures are equivalent if and only if two parameters match each other. And you can tell that this is why we conjecture that in R4 is this case. Recall that in Euclidean space, when d is greater than or equal to 5, this is known, but when d is equal to 4, this is unknown. On manifold, we show that when d is equal to 4, it's the same as d greater than 4. So that's why we conjecture in Euclidean space, R4 is the same as R5, etc. And also we show the Rbf kernel, two measures are equivalent if and only if they have the same parameter for any dimension d. And when d is 4 here, and for the Rbf kernel, these two are open in Euclidean space, and that's why we make the conjecture in Euclidean space. Okay, and why we can show this d equal to 4 and Rbf kernel is because we have only if. So we know what happens if the series is equal to infinity, and we can do some proof, unlike the Euclidean space. So any questions here?
So one question from my side is that, do you assume that your covariance or your Gaussian process is represented as a series with respect to Laplace-Beltrame eigenfunctions, or do you do these multiplicities of eigenvalues come up like without the explicit assumption of this form?
No, this is for general Gaussian process. It can be written in any form.
Yeah, so, yeah, okay. And another question is that it's something on background work, actually. So I know that there are, in classical theory, there are two regimes of data collection. So basically the fixed domain, which you consider, and there is another one, which I don't remember how is it called. But basically you can choose your data points such that they are going to infinity asymptotic.
Yeah, that's the increasing domain or outfield domain usually. Yes.
Yeah, and so in the classical setting, do we have something better if we transition to this increasing domain setting?
Yeah, that's a good question. So at least Euclidean space, the increasing domain, I mean, the asymptotic theory for the increasing domain is sort of easier than the fixed domain.
I'm sorry, what can you say again?
The increasing domain is easier in some sense than the infill domain in the Euclidean space case.
So can you get better properties?
Yes, and we have some. We know more for the increasing domain. Yes. And
it's just
so for
intuitively very tempting to assume that in Euclidean setting we have problems because we restrict it onto a compact part of the big non-compact space, and here we just have a compact manifold, so we have basically the whole space.
Exactly. Yeah, that's a really good question. So I'm not quite sure how to define increasing domain on a compact Riemannian manifold, right? For example, on a sphere or a circle, what's infill, what is outfill? It's hard to say, right?
Seems natural that they just coincide and there is only one setting there.
Yeah, exactly. Yeah.
So,
yeah, sure. Go ahead.
I think the big difference with respect to the previous case is that here you have a discrete structure.
Yes, exactly.
Once you have a discrete structure, everything reduces to the comparing of two Gaussian sequences.
Yes. Exactly. Yeah.
You just compare the coefficients with respect to a fixed base.
Yes.
And this is very, very well studied for Gaussian case, the equivalence of such things.
Yeah. Thanks for the comment. Yes. This seems easier than the continuous case. That's why we have stronger result here.
So basically, you use the Carhunian law of decomposition, and this makes things easier. But the question that comes to mind is that, can you use this maybe in the fixed domain Euclidean setting by restricting your process onto this fixed interval and considering the compact process with Carhunian law of decomposition there to achieve something?
Yeah, that's a good idea.
I don't know. It's just
Yeah, I think it's worth a try.
Oh, Slava, I'm afraid this doesn't work like this. If your basis depends on the parameters. If it does not, then everything is fine. But if it varies with parameters, then it should not be that nice as we would like.
Yeah, I see. So we don't have like the fixed basis that in which we can compare
in your setting, you still have this fixed base, right?
Yeah.
So for arbitrary processes, it would not work like this. But if all the family of the process you consider hangs on the same basis, then it would work.
Yeah, I see. Thank you.
Okay. Yeah. Thanks for the comments. And then I'll briefly talk about the four phenomenon, why four is important. So recall the Euclidean case, the integral test degenerates to this integral at the end. For the Matérn case, I mean, or for the Matérn case. So it's essentially integral of 1 over x norm to the 4. And we know that this is integrable if and only if the dimension of the Euclidean space is less than or equal to 3. This is just calculus. And when d is greater than or equal to 4, we know that this integral is equal to infinity and the integral test fails. We don't know what happens if the integral is equal to infinity. And then when d is equal to 4, under this paper, they construct the theta n hat directly. It didn't show any systematic tool for the case where the integral is equal to infinity. They just construct it directly. Very complicated and highly non-trivial construction. But when d is equal to 4, this construction fails. And this reminds me the ununique smoothness or the differential structure in R4. I don't know whether there's a relation between this or not. And for the manifold case, at the end, we will have for the Matérn case, we will have this sum of multiplicity times lambda n to the -2. Lambda n is the eigenvalue of the Laplacian operator. And so in order to make this series converge, we need this lambda n grows faster enough than Tn, right? But there's a Weiss theorem says that there's a strong relation between the multiplicity and the eigenvalue itself. So the number of eigenvalues less than or equal to n is asymptotically of order d over 2. So that's why the dimensionality on mental case also comes in. Basically, this dimension controls the relation between Tn and lambda n. And it's not hard to show that if both Tn and lambda n are just polynomial, these two are both polynomials, then this integral, this series is finite if and only if lambda over d is less than 2. That is, d is less than or equal to 3. And similarly, when d over 2 is greater than or equal to 2, this series is equal to infinity. So that's why the dimension of the manifold is still useful. So for the Euclidean case, this just comes from the integral, naturally from the calculus result. For the manifold case, it comes from the Weiss theorem. And yeah, this is an open question, I guess. I don't know how to relate this.
Excuse me, but where do we get this integral of 1 over x in power 4 from?
Yeah, this is, so in the integral test, you plug in F2 and F1 as the Matérn spectral density, and you do some like Taylor expansion. You'll see that the main term is this.
Oh, yeah, I see. All right.
Yeah. Other higher order term doesn't matter, so just we care about this term. Okay. And similarly for the predictor BLUP, we have a misspecified alpha 1, and we use the MLE of a sigma 0 square. We have a closed form, and we care about the BLUP. And we see the parallel results. So the first, we show that the microergodic parameter is consistent with probability 1 under P0. And we show that the MSE of the wrong BLUP is the same as the true BLUP, and the wrong MSE is equivalent to the true MSE. So that we have already seen this Euclidean space. We just show the parallel results. I will not repeat it again. But what is missing here is that the normality. In Euclidean space, we show that this one converted to a Gaussian distribution in distribution. But for the manifold case, we cannot show this, unfortunately. So the proof in the Euclidean case highly depends on the linear structure of the Euclidean space, and also the Fourier basis e to the ix. That function is super useful. But for the manifold case, we lose that. What we have instead is the eigenfunction fn. Fn is just abstract function. We know nothing about fn. So this proof is still missing. We make it a conjecture, but we did some numerical experiments. It does convert to n0 too. It is normal, and we check the variance. It's still like 1 over square root of n, but we cannot show it, unfortunately. These are just some parallel results to Euclidean case. Not that surprising. So I will finish this talk by 2 simple examples. I just steal this result from Slava's paper. So when M is a circle, and we know that the eigenvalue of a circle is n squared, when U is 1/2, which means it's the exponential kernel, and we can write the covariance function and the spectral density in a clean way. This is tangent h cosine h, the hyperbolic tangent hyperbolic cosine. And then the Rbf kernel depends on this so-called Jacobi zeta function. And this is a spectral density of the Rbf kernel. And here's the figure of this kxy S1 with nu equal to 1/2. And we can see that this it reaches the minimum when the distance is 0.5, which means these 2 points x, y are antipodal points, north pole and south pole. And here is some realization of the Gaussian process on S1. You can see that the bigger alpha, the faster decay of the spatial dependency when 2 points are far away from each other. That's why it's very bumpy. But here it looks better. So for 2 neighbors, they have similar values. Okay, and then for another example is S2, and also we know that the eigenvalues are n times n plus 1, and Fn are just some of the spherical harmonics. And for any smoothness parameter nu, we can still write down the covariance function k, the spectral density, where the covariance function depends on the legendary polynomial, and similar for the Rbf kernel. These are all from Slava's paper. And also I steal a figure from their paper. So this is a kind of unknown manifold where the domain M is the surface of this dragon, and which is unknown. So you don't know the eigenvalue or the eigenfunction. What you have is that you can estimate the eigenvalue eigenfunction by the graph Laplacian, etc. There are many existing series on this side. So once you have the approximation of this eigenvalue eigenfunction, you can approximate this k, and you can just do some standard Gaussian process, and we have these beautiful results. Okay, so that's all for the theoretical part, and there are many open problems in this direction. The first one is that we have many conjectures left in the paper. For example, in Euclidean space with dimension 4, what happens to the microergodic parameter of Matérn? What happens also for a general Euclidean space? What happens to the Rbf kernel? These are both unknown, and also for our manifold setting, whether the microergodic parameter is asymptotically normal is unknown. Okay, and then we are assuming this nu is known throughout this talk. And why is that? Because even in Euclidean space, if we include this nu in the unknown parameter, the MLE is very complicated and numerically it's super unstable if you want to estimate this nu by some numerical solution to the MLE. And also whether we can consistently estimate this nu is unknown in Euclidean space. But actually I forgot to mention on the manifold case, we can show that this nu can be consistently estimated. I forgot to add it to the talk. So actually it comes from the only if part of the series test. So
is
that
this,
means
sorry to interrupt, is this, does this depend at all on the dimension of the manifold, or is it true that it can be consistently estimated with any dimension?
you mean the nu or?
On the manifold case, yeah, the nu.
Yes, it doesn't depend on the dimension. We can always consistently estimate this nu.
Okay, thank you.
And in the
Yeah,
same,
but,
so do we estimate all? So we assume that we know we know true parameters alpha and sigma, and then we can consistently estimate nu.
no, it's just from the equivalent of measure result. So two Matérn GP are equivalent if and only if nu1 equal to nu2 and sigma square over C alpha equal to sigma square over C alpha 2.
And can you show that if you use maximum likelihood, then the nu estimator converges to the true value of nu?
I don't think that's true.
Hmm.
Yeah, because the MLE is so hard to deal with when nu is also included. And also people try some numerical estimator of this nu. It's hard to tell, it's super unstable. So I suspect the MLE of nu is consistent or not. My guess is no.
Mm-hmm. Okay, yeah, thank you.
Yeah, so in short is that in Euclidean space, everything regarding nu is unknown, it's open. For manifold case, we know some results about nu. And also the scalability on manifold, I skipped that part. So there are some scalable version of Gaussian process like the tapering GP or nearest neighbor GP, whatever. So they make the covariance matrix sparse so that you can calculate the inverse or the further operation on the inverse easily. And those methods are designed only in Euclidean space. So I wonder if we can generalize those scalable version on manifold. And also, so as mentioned in Slavi's paper, so usually in practice, you don't know the manifold. So you have to approximate the Laplacian, the eigenvalue, eigenfunction. So that means you are introducing more approximation error. So what happens, like, can we combine the this geometrical error and the error from the GP side? And can we develop some new series on that side? And also, there's a following up paper by Slava. It's a beautiful paper on graphs. So I'm curious about the parallel results on GPs on graphs. So as you mentioned, so it's essentially a finite dimensional distribution if your graph is finite, right? So if graph is infinite, so it's essentially a Gaussian process. It's a true GP. And what happens in this case? And I suspect that these parallel results still hold once you have the Laplacian. Once you have the Laplacian, then you can define the, I guess in your paper you define the Matérn kernel and the Rbf kernel, right? And but again, we need to show a series test or whatever. We need a condition to determine whether two measures are equivalent. That's the key. That's also open, I believe. Yeah. So that's all for my talk. Thank you.
Yeah.
So thank you very much for the talk. And thank you for presenting the kind of open questions. Obviously, there is a lot to be done yet. Yeah, so now I'm gonna stop recording and we will have some time for questions.